Hello everyone, I'm Xiayu from the University of Illinois, Urbana-Champaign. I'm a PhD student supervised by Dr. Houtan Jebelli. Unfortunately, due to my visa processing delay, I was not able to travel from the US to Canada to join you today in person, and I apologize for that and appreciate your understanding. So today I'll be presenting our work on adaptive kinematic and dynamic control for hexapod robots in complex construction environments. And this research addresses a critical need in the construction industry for safer and more efficient inspection methods. Roofing is one of the most dangerous occupations in the construction industry. According to the Bureau of Labor Statistics, roofers faces extremely high fatal work injury rates, among the highest of all occupations. Beyond safety concerns, the industry faces severe labor shortages, with over 12,000 openings projected annually from 2022 to 2032. The traditional approaches also suffers from time-consuming training requirements, high labor costs, and quality inconsistencies. These challenges present a clear need for innovative solutions. Researchers have explored robotic alternatives, most through UAVs or drones and UGVs or ground vehicles. However, each has significant limitations. UAVs offer advantages like safer operation, but suffer from restricted perception capabilities, limited visual quality at distance, regulatory constraints, and short battery life. UGVs addresses many of these limitations through enhanced perception capabilities, close-up inspection abilities, fewer regulatory hurdles, and longer operational durations. Among UGVs, design include wheel-based, track-based, and leg-based systems, each with their own advantages. While existing UGV solutions show promise, there still remain significant research gaps. Current UGV solutions still experience perception limitations and safety issues, particularly regarding navigating roof slopes, detecting edges, and avoiding collisions. So our solution was inspired by the Spider-Man. We aim to bridge these gaps by developing a specialized hexapod robot system, which has 6 legs that can stably navigate and inspect roof structures. So the key innovation is combining adaptive kinematic with dynamic control in a leg-based platform. Our system consists of 2 major components: the robotic platform with integrated sensors and the control system. The platform uses IMU, TOF, and infrared sensors to perceive its environment. The control system has 2 primary modules. The first one is the gait stability enhancement module, and the other is the slope posture control module. The gait stability enhancement system using Bézier curve-based trajectory generation for smoother, more energy-efficient leg movements compared to traditional trajectories. The slope adaptive posture control system using a fuzzy PD controller that can dynamically adjust leg motor angles based on center of gravity arrows. We use the mutual hexapod robot with 18 degrees of freedom, 3 per leg. So the robot measures 465 millimeters in length and 514 millimeters in width. Each leg has 3 segments: coxa, femur, and tibia. We established coordinate frames for kinematic modeling and implemented both forward and inverse kinematics for precise motion control. The robot uses a tripod gait for stability. 3 legs always maintain ground contact while the other 3 swing forward. Our key innovation is maintaining the center of gravity within the conservative support polygon using real-time adjustment. Here we can see our fuzzy control implementation. We use membership functions for arrows and arrow derivatives. with fuzzy rules determining proportional and derivative gains. The fuzzy PD controller adapts gains based on error magnitude. Smaller gains for large errors to prevent overturning, and larger gains for fine-tuning when errors are small. This adaptive approach outperforms traditional linear PD controllers, especially on inclined surfaces. For evaluation, we equipped our Hexapod with multiple sensors, including an IMU for orientation detection, TOF for positioning, and infrared sensors for edge detection. The control system continuously monitors the support pattern and projected center of gravity to ensure stability during a movement. So we evaluate our system through extensive simulations. The test 1 evaluated the performance on 3 roof pitches, which are 2/12, 4/12, and 6/12. These represent common residential roof slopes. So test 2 assessed the robot's ability to navigate structural transitions, ridge lines at 30-degree angles, valleys at 135 degrees, and flashing interfaces with 10 millimeters elevation changes. So these represent critical challenges in real roof inspection. Our results show significant improvements. On 2/12 pitch, we achieved 21% better stability margin compared to the default control system. The improvement was 15% on 4/12 pitch. Remarkably, on the steepest 6/12 pitch, our system maintained stable locomotion while the default system failed completely. Body orientation control showed excellent performance. Height variations were maintained much lower with our control. Roll angle stayed within positive and negative 2 degrees, even on the steepest slopes. Pitch and vertical acceleration variations were more stable with our control. For structural transitions, we see the pitch and roll responses during ridge, valley, and flashing navigation. Our control system maintains much smoother transitions with smaller deviations. Quantitatively, the success rate of 10 trials for each subtest of our system outperforms the baseline. Crossing times were also reduced by 25 to 33% across all transition types. Here we can see video comparisons of our system versus the baseline, navigating these transitions. Notice the smoother, more stable movement with our control system with a higher success rate. In conclusion, we have developed an integrated control framework that significantly enhances Hexapod robot performance in construction environment. Our contributions include the novel integration of adaptive fuzzy PD control with Bézier trajectory generation, 21% stability improvement with 8 to 100% success on structural transitions, and specialized control for construction inspection tasks. Limitations include simulation-only validation and reduced performance on extremely steep slopes. Our future work will focus on real-world validation, algorithm enhancement for steeper slopes, and improving energy efficiency for extended operations. So this research advances the development of autonomous inspection systems in construction, potentially reducing workers' injuries and improving inspection quality. And here are our references for those interested in learning more about this work. At the end, thanks for all your attention. I'm happy to take any question or get connected via my LinkedIn. Please feel free to reach out. Besides, I'd like to express my sincere gratitude to the ISARC conference organizers. Also, thanks to our funding agencies, my PhD advisor, Dr. Houtan Jebelli, and all the members of the RACE Lab. Thank you.